Hey guys, so today we're here to talk about the equivalence of mass and energy. In 1905, famous physicist Albert Einstein used his work on special relativity to derive one of the world's most famous equations, E equals mc squared. Special relativity is the propagation of light and matter at high velocities. If you would like to learn a little more on special relativity, you can go to this link provided. But we are going to continue as though you have a basic idea on this topic. It's a good idea to familiarize yourself before we proceed. Through Einstein's equation, we can see that the mass of an object is simply an object's energy divided by the speed of light squared, which is 2.99 times 10 to the 8 meters per second. This equation changes everything. As before, energy and mass were regarded as completely different entities.
If we look at the law of conservation of mass, we realize that in an isolated system, mass cannot be created nor destroyed. For example, in a chemical reaction, the mass of the reactants is equal to the mass of the product. Similarly, the law of conservation of energy states that energy cannot be created nor destroyed. That is to say, the total energy of an isolated system is constant, and we know that number to be the sum of the kinetic and potential energies. However, in some reactions, scientists notice a loss in energy or mass within a system, which would violate the laws of conservation of mass and energy. How can this be possible? This is because within a system, energy can be converted into mass, and mass can be converted into energy.
A great example of this topic shown by Mr. Anderson from AP Science is carbon-12. We know that carbon-12 is a standard upon which we figure out what an atomic mass unit is. Carbon-12 has exactly 6 protons, 6 electrons, and 6 neutrons. And if you were sharp in chemistry, you'd be able to figure out that it has an atomic mass of exactly 12. Now if I were to take that carbon-12 and deconstruct it into its subatomic particles, we should get 6 electrons, 6 protons, and 6 neutrons. And if I were to add up those masses, we should get 12, right? Let's find out. We know the atomic mass of each electron, so we multiply that by 6, and then multiply the atomic mass of protons by 6, and then 6 times the neutrons, and we should get a total of 12. But wait, we get a slightly higher number. And this is because the energy used to hold the protons and neutrons together are converted into mass.
The previous example was of energy being converted into mass. But what about mass being converted into energy? The most common example of mass being converted into energy is that of the atomic bombs dropped on Nagasaki and Hiroshima. But how much mass is needed to release that much energy? The answer is not as high as you might think. In fact, only 700 milligrams of mass was converted into energy during the Hiroshima bombing. The reason that very little mass is needed for a huge amount of energy is found in the original equation. As we can see, the energy is equal to the mass multiplied by the square of the speed of light, which is a very high number indeed. Thanks for listening. We hope the presentation hasn't been too technical or boring. Please check out some of the sources listed in our bibliography for more information. Once again, thank you for listening.
Created using Powtoon.